In module 3, we're going to see how can we build multivariate probability density function from the knowledge of the marginal random variable and a correlation matrix that will link them together in order to model the dependency between these random variables. So why would we want to do this? When we want to attack a structural reliability problem, we need to model the joint probability density between all the variables involved either in the resistance or the loading model. But these variables might be dependent upon each other. So we want to be able to represent from our knowledge of the marginal random variable what is going to be the joint while including the correlation that might be included between them. So for instance, if x1 is gamma, x2 is log normal, and the correlation coefficient is 0.6, how can we model such a joint probability density? For the normal or the log normal, we directly add access to a multivariate correlated joint PDF, but we didn't intrinsically have access to this for different marginal distribution. And this is what we want to do here with module 3. How to define both the joint PDF and joint CDF for these multivariate PDF or CDF, where we're going to be able to prescribe some correlation between these random variables. So we're going to look in this module at the Morgenstern methods to make these joint distribution, or the Nataf method. And then we're going to look at a summary of what we looked at. And we're here in the last module that is related to probability theory. How do we build joint PDF from knowledge of the marginal and correlation between them? So the first method we're going to see is the Morgenstern method. So we're going to see how do we define with Morgenstern method both the CDF and PDF. So we're going to see, we're going to first define the CDF and then we're going to derive the formulation for the PDF. We're going to see how from a correlation coefficient rho, we can define the parameter of the Morgenstern distribution, which is alpha ij. Then we're going to extend for the multivariate case for more than 2 dimension, and we're going to look at example application and the specific properties associated with the Morgenstern method. So first, let's look at a bivariate case. So let's say we have two random variable x1 and x2. So the Morgenstern joint CDF is defined as follows. We're going to have the product of the marginal CDF for x1 and x2 times everything we have here, 1 plus alpha 1, 2. Alpha 1, 2 is going to be the Morgenstern parameter that controls the dependency between my two random variables, times 1 minus the CDF of x1 times 1 minus the CDF of x2. So this is the mechanics behind the Morgenstern joint distribution. And keep in mind, we have already saw that if we evaluate a joint CDF at the upper bound, we're going to marginalize that variable. If we evaluate at the other variable, we're going to marginalize, in this case, x1. And this is the same here. If we evaluate f of x1, x2 for the joint Morgenstern CDF at, say, infinity here, so this thing is going to be equal to 1. So I'm going to just be left with my first CDF. And if I evaluate this at the upper bound, 1 minus 1 is going to make 0. All this term goes away. Okay, so we see that this satisfies the property of a joint CDF still. And if we take this formulation and we differentiate it with respect to x1 and x2, we're going to get a closed form solution following this for the joint PDF that still maintain a very simple and elegant analytical solution where the joint CDF, according to Morgenstern, is going to be the product of the joint, the marginal PDF, f of x1 and f of x2, times 1 plus the same alpha 1, 2, the parameter that controls my dependency, times 1 minus 2 times the marginal CDF, 1 minus 2 times the marginal CDF for x2. And where I told you that alpha controls the correlation coefficient, in order to remain admissible, that alpha 1, 2 must be between minus 1 and 1. Otherwise, you're going to have nonsense result here when you're going to have probability density that is greater or lesser than 1, or you're going to have here a CDF that is above or below, above 1 or below 0. So we need now to find what is the relationship between our correlation coefficient rho 1, 2 and alpha 1, 2 that is used in the Morgenstern distribution. So to do this, we need to look at the formulation for what is the correlation coefficient. In the two-dimensional case is the integral with respect to x1 and x2 of x1 minus mu1 divided by sigma 1 times x2 minus mu2 divided by sigma 2, weighted down by the joint PDF for x1 and x2. So in this case, we're going to approximate that relationship where rho 1, 2 is going to be equal to 4 times alpha 1, 2, q1, q2, where these q1, q2 are given by these relationship here. And so we can reverse these relationship to say that my alpha 1, 2 is going to be equal to rho divided by 4 q1, q2, where these q1, q2s are defined according to what type of distribution am I looking at. So for some distribution is a constant, some other one is some formulas that are defined according to the parameters of the distribution. That was for the bivariate case. How can we generalize to an n-dimensional case? It would look like this. So we would take for the joint CDF, the product of the marginal CDF times 1 plus, we're going to take the pairs of term and we're going to sum for all pairs of term. So again, I lesser than j, we don't want to permute the term. We don't want the term ij and ji to be taken twice. So it's only each pair of term taken separately without permutation, where we're going to have the same ij we saw. Then we need to sum for all the triplets of terms and all the quadruplets and so on. And it's a very similar formulation for not the CDF, but this time the PDF. But here we're going to need to see what are these terms, the alpha IGK and IGKL, for instance. So that alpha IGK is the correlation coefficient 1, 2, 3 k divided by 2 to the power k divided by the product of the qk's, where that rho 1, 2k is the expected value, not only for 2 term, but the expected value for n term, where in practice, that correlation coefficient with more than 2 term is assumed to be 0. Okay, so that all these higher order terms that we saw here will drop in the formulation of Morgenstern. So we're just going to be left with that formulation where we're going to have the sum of these pair of terms. But one of the main limitation of that Morgenstern method is that it will only allow for a limited range of correlation value. So in this case, it's going to be lesser than no less than 0.33 and no greater than 0.33. So that's going to really make a limited range of values that we can use for the correlation coefficient. So let's look at an apply example where we're going to say that our first random variable we want to model is going to be a Rayleigh distribution, so given by this PDF and given by this CDF, where the parameter sigma 1 is going to be equal to 1. Our second random variable x2 is going to be log normal with this PDF and this CDF, where we're directly going to give the parameters. So lambda, the mean in the log space, is going to be 0. Zeta, the standard deviation log space, is going to be 0.3, where we're going to say that my correlation coefficient is 0.307. So we're going to model that joint CDF by the product of the marginal times 1 plus alpha 1, 2. We still need to find that parameter that controls my dependency from my correlation coefficient. We cannot directly use it. We need to find it for the Morgenstern distribution as the rho 1, 2 divided by 4 q1, q2. So we're going to have a q1 for my log normal, a q1 for my Rayleigh. We're going to come back to this. Times 1 minus 2 times my CDF for x1, so CDF for x1, times 1 minus 2 times CDF for x2, I have my CDF for x2. So if we look at this, so I have my joint distribution from the Morgenstern method. We have the marginal PDF for x1 times the marginal PDF of x2 times 1 plus alpha 1, 2, 1 minus 2 CDF of x1, 1 minus 2 CDF of x2. And the only thing I need now is to find alpha 1, 2. As we said, it's going to be the correlation coefficient, 0.307, divided by 4q1 times q2, where these q1, q2 are defined according to the distribution we had. So if we look at here, distribution for the Rayleigh is going to be 0.280, so it's fixed. And for the log normal, we need to evaluate that expression. That is function of the CDF of zeta and exponential of zeta here, and it should be no greater than 0.282. So in this case, if we evaluated that alpha 1, 2 is going to be 1. So we see we're already with 0.307 at the upper bound of what we can evaluate in terms of dependency for that Morgenstern. So the joint PDF would look like this. We have the marginal for x1, the Rayleigh, the marginal for x2, the log normal, and the joint would look like this. The contour of that surface would look like this one. So if we explore a little more, so we see that the same result here, we can evaluate for a correlation coefficient, say, of something very close to 0. So it will look like this, and this would be analogous to obtaining the joint distribution by making the point multiplication of my marginal at every location where I want to uh, obtain my joint PDF. Then if I look at, instead of 0.307, I'm going to look at 0.5307. So in that case, oh, I still got a result, but is my result admissible? Okay, if we look at that joint PDF, so look here what happened for, oh, sorry, I'm not with a good example. I skip a beat. So let's look at 0.53. So we still got a joint PDF, okay? But look at what's happening here. So in this case, I have some value for my joint PDF that are negative. So negative PDF values are definitely not admissible. My joint CDF is going to be biased as well. It's not going to sum to 1 as an upper bound or 0 as a lower bound. So same thing, if I look at 0.93, it's going to be even more extreme. So you see, I'm going to have very large negative value. We're outside of the range of admissible value for my Morgenstern distribution, which is limited to a fairly narrow admissible range. So if we look at the properties of that Morgenstern distribution, we can say that it's compatible with any set of marginal distribution, so it's widely applicable. However, the range of correlation coefficient that we can use is in a narrow bound that is roughly minus 0.33 to plus 0.33. Now, the Nataf distribution is going to allow us to extend and to build upon these limitations. So first, we're going to look at the definition. What is a Nataf distribution? How do we define the correlation with this method? Example of application, and again, what are the properties associated with it? So let's assume we have a knowledge of, for a set of n random variable, of the marginal PDF for each of those variables. They don't have to be the same, they could be any mix and match. Then the first step we need to do if we want to use the Nataf method is going to be to transform each of those marginal distribution in a standard normal random variable. Okay, so what do we say? Z is going to be a standard normal, so a normal PDF would mean 0, variance 1. And we saw in the revision for probability theory that we can do so, or sorry, we saw that in the revision about probability distribution, that we can transform a random variable in the standard normal space through the equality of the CDF. So I'm going to have the CDF for my standard normal random variable Zi must be equal to the CDF of my ith random variable. So we saw this for a Gaussian, but this is also available for any marginal PDF. So if I want to have my Zi, the only thing I need to do is to send my CDF on the other side of the equality by taking the inverse of the CDF. Okay, so I take inverse CDF on this side, inverse CDF on the other side. So the inverse of my standard normal CDF of my CDF of xi is going to tell me where's the mapping between xi and zi. So the corresponding space from my original coordinate to my coordinate in the standard normal space. So we saw this in module 1. I have to go from a Gaussian random variable into a corresponding location in my standard normal space. And we saw that by equality of the CDF, I add a linear mapping between my original space and my standard normal space. In the case of an arbitrary distribution, this is what we have on the right, we have again that same possibility of doing the mapping. So going from my original space, so a given x, I'm going to take a value, I'm going to read it in my CDF, and I'm going to read from the inverse CDF of my standard normal space. I'm going to have the corresponding value, okay, where both are evaluated for a CDF of 0.77. So from a coordinate of 2.09 in my original space, that corresponds to 0.74 in the standard normal space. And this can be done for any arbitrary distribution in my original space. And the specificity is that for a Gaussian transformation, so if I have a Gaussian going to standard normal space, the mapping between any value is going to be linear. Whereas for an arbitrary distribution that is not Gaussian, we're going to have a nonlinear mapping between my original space and the standard normal space. So what we're going to do then, so once we've completed that mapping from the original distribution to the standard normal space, we're going to use our change of variable rules to go back to the original space. So keep in mind, X is the original space where we want to work our reliability analysis, and Z is my standard normal space. And we saw earlier that we have this equality in this change of variable rule. We saw this in the revision module for probability theory. So we saw that f of x dx must be f of z dz. So the probability content in neighborhood between two different spaces must be maintained. So it means that if I want f of x and I have access to f of z, I send the dx on the other side of the equality, and I can evaluate this. So now what I did by transforming into my x variable into standard normal space, I obtained the marginal distribution for this thing. But what I can do is that since this is a standard normal, I have access to a closed form solution for a correlated version of that joint PDF. So what it means, I can define my joint PDF from the knowledge of the marginal I just transformed, plus the correlation coefficient that I'm going to use to define a jointly normal distribution for f of z. And then I'm going to transforming back to the original space by simply applying this change of variable rules, where this represents the determinant of the Jacobian, because what we see here, dz dx, is a Jacobian matrix, which represents the partial derivative of each ith distribution for the z space up to the original x space. Okay, so if I have n variable, this is going to be a n by n matrix. And since each of those transformation for a zi, it only involves a single xi. So it means that this Jacobian matrix is going to be diagonal. I'm going to have only non-zero term on the main diagonal. And the determinant of a diagonal matrix is going to be the product of the term on the main diagonal. And so the last thing we need to define is what is dz dx. So dz dx, if we look at dimension one by one, we're going to see that we have a simple solution for this. So for f of z, we said that we're going to have that joint standard normal correlated space, where we're going to define that correlation according to the correlation coefficient we want to achieve. And here, the determinant of the Jacobian is simply the product of the term on the main diagonal of my Jacobian, where dz dx here, you see that it involves two CDF. Remember, the derivative of a CDF is a PDF. So I'm simply going to have the ratio of my two PDF, the PDF for my original space divided by the standard normal PDF for ZI. And for the CDF is directly modeled by the CDF of my correlated space here. So the only thing that remains to us to be able to apply the Nataf distribution is to find what is going to be that R0 correlation matrix, okay? Keep in mind, R is the correlation matrix in the original space, which is not going to be exactly equal to the correlation in the standard normal space. So that R0 takes the same form as the standard correlation matrix. So we're going to have 1 on the main diagonal, the correlation coefficient on the off diagonal term, and it's a symmetric matrix. And this rho ij, the one we have from the original space, is a function of rho 0 in the standard normal space. We can again define it here from that standard formulation for the correlation coefficient is going to be the integral in 2 dimensions for zi zj of xi minus mu I divided by sigma I, and the same thing for the other variable, weighted down by my joint PDF that is defined with my correlation coefficient rho 0. And in general, that rho 0 is lesser or equal in absolute value than the original one. Sorry, it's greater or equal than the original one. But there's no direct solution to evaluate it, okay? So what we can do is we can do an inverse numerical resolution, and these approximate results are available in table. In modern codes such as Pistra or Pyri, they're going to directly make the numerical resolution without necessarily to looking at in table R we're going to see here. So if we look at table, we're going to say that rho 0 is going to be equal to a constant times rho ij, where that constant is greater or equal to 1. So what is going to be that C value? It's going to depend on what is going to be the type of variable for xi and xj. So if it's both are normal, it's going to be 1. If it's going to be normal and group 1, it's going to be a constant. Normal group 2, a constant that is function of the coefficient of variation. Group 1, a constant that is function of the correlation coefficient. Group 1, group 2, a constant function of correlation coefficient and coefficient of variation for the second variable. And group 2 is going to be a function of the 2 coefficient of variation. Correlation coefficient is again going to return a constant. So group 1 are the PDF that are can be normalized linearly, and group 2 can be linearized non-linearly. So group 1 is going to be normal, uniform, exponential, Rayleigh. Group 2 is going to be log normal, gamma, and other joint PDF. If you look at here a visual representation of the relationship between rho ij and rho 0 ij, so this is for the standard normal space, this is for the original space, we see that there's a very close correspondence between the two. So in the positive domain, both are going to be negligibly close to each other, the two correlation coefficient. We might see some discrepancy if we go in the negative domain. So if we look at the value for the table, so if we have xi that is normal, xj group 1, xi normal, x2 group 2, we see the formulation. We have again for xi, xj group 1, we have xi group 1, xj group 2, xi, xj group 2, and that's it. So we can find, depending on what value you use, what is going to be the relationship you need to use to compute that C coefficient that's going to multiply your correlation coefficient. And now if we look at what are the admissible bounds for correlation coefficient, according to what is going to be the marginal distribution, it's much wider than what it was before. Okay, so that's going to open the door for application that are much more realistic in practice. So let's review our example where we have two a marginal random variable. The first one is going to be Rayleigh, PDF, CDF. Parameter is sigma 1 equal 1. And x2 is again log normal. We have the PDF, we have the CDF, and we want to use a correlation coefficient of 0.307. So we're going to model this by a joint bivariate standard normal PDF, sorry, where R0 still has to be determined from our C coefficient and 0.307. And this is going to be the product of the marginal f of xi, s of x2, divided by the standard normal phi. So if we do this, we're going to have the product of the marginal f of x1 times f of x2, these two. So we directly have the solution for these, times the bivariate joint distribution in the standard normal space. So we have this, which is function of rho 0. We still have to determine this one, divided by the product of phi z1, phi z2. But here, keep in mind, this is evaluated for x1, x2. Where do I get those z's? Okay, I want to evaluate this for x, not for z. So these are obtained, these z's, from that mapping between my original space x and my standard normal space. So I'm going to evaluate the x I want to evaluate to in its CDF, and I'm going to evaluate the inverse standard normal CDF for that result. I'm going to obtain the corresponding z. So I can directly use the z1, z2 that maps from x1, x2 in this formula. And my c, my coefficient is going to multiply my correlation coefficient to obtain rho 0. This formula that involves the correlation coefficient, the coefficient of variation for my second variable, is going to be obtained from the table here. So I'm going to have one that is log normal. The second one is Rayleigh. This is the equation we're using to find the C value. So row 0, 1, 2 is going to be C 1.024 times row ij 0.315. So it's very close to the original value we had. So this is how it looks like if we go and look. So we can see that this is how the joint PDF looks like. So we can see here we have our marginal distribution, the joint. And now if we look at something that is going to be, it's going to be more like this, 4.307, looks like this. If I evaluate at 0, this is going to be equivalent to if we would have obtained the joint PDF from the product of the marginal. And if we evaluate for some high value, say 0.83, we can see that we can now impose much higher correlation coefficient for, sorry, a much higher correlation coefficient and still have an admissible PDF. We don't have the negative value problem as we had before. So this is what we're going to be using in practice for most applications. So the property of the Nataf model is that it's compatible again with any marginal PDFs from which the CDF is monotonically increasing and is differentiable. So we cannot have step in or CDF, but for most distribution we want to use, we're going to be able to satisfy that hypothesis. And the range of value for the correlation coefficient is not from the full range of -1 to 1, but is wide enough to accommodate most practical situation we're going to face in structural reliability problem. So in summary, for the Morgenstern distribution, its formulation was derived from the formulation of the joint PDF that we differentiated to obtain this. And then we just have to define that alpha parameter from this formulation where Q1, Q2 depend on the choice of the marginal distribution. It's easy to work with, but the problem is that it has a limited range of correlation coefficient. We can use it to satisfy that alpha is going to remain between those bounds. On the other end, the Nataf distribution, the principle is going to be we're going to transform each of our marginal distribution in the thinner normal space. Then we're going to define the joint distribution in the thinner normal space by correlating it and then transforming it to the original space using the change of variable rules. So it's going to be that joint PDF in the standard normal space that is correlated times the determinant of the Jacobian that will give us this term here. So the product of the main diagonal term of our Jacobian divided by the derivative for my CDF, derivative of my CDF, which are going to be the PDF for the original space divided by the PDF in the standard normal space. And the relationship between my correlation coefficient, the original space, and standard normal space is obtained from a constant times this value, where we can again get the constant as a function of the marginal distribution we want to pair together. And the main advantage we have with the Nataf is that we have now access to a much wider range of correlation coefficient we can use it with. So that closed that first part where we were looking at aspect related to probability theory. We can now move on to our first method where we can really evaluate probability of failure. The next module is going to be about Monte Carlo methods for estimating probability of failures.